So the rest of today, I want to go through what are the main or the conventional steps for pre-processing fMRI data.
So as you remember, each volume is acquired a slice at a time, thanks to the slice selection gradient. Now you'll also remember that a full volume, therefore, because we acquire it one slice at a time, takes a certain amount of time in order to be acquired. Just to give you an example, imagine we were to acquire a full volume in 30 slices, and let's imagine that our TR is 2, so it takes us 2 seconds to get a full image of the brain. Essentially what we're doing is the following. We would, at the beginning of the TR, we would acquire this slice of data. Then a couple milliseconds later, we would acquire this slice of data. Then a couple hundred milliseconds later, this slice, and then this slice, and this slice, et cetera, et cetera. Right? And it's taking us time to acquire these data. In fact, just to acquire half the data, it's taking us half the TR, that is to say 1 second. Because after this, we're going to acquire this slice, right? See the slice down here, the slice in between. See, we're taking the slides in a so-called interleaved fashion. So we first take all the odd slices, and then we take the even slices. Okay, this is how we cover the full brain. And then this slice, and then this slice, and this slice, et cetera, et cetera. In other words, it's taking us 2 full seconds to sample the bold signal across the whole brain. Now, if you think of it in neural terms, 2 seconds is a ton of time, right? So we think we're taking the picture of exactly, in that one moment, what is the brain doing right now? But that's not what's happening. We are sampling the brain as neural events start and end, and we kind of nibble at it over time. Let me show you an example of this. Imagine that we are acquiring slices of the brain, just as seen here, in an interleaved order. Okay, I'll get back to that in a second. And let's say that we care about this little piece of the brain right here. In fact, let's assume that this piece of the brain, all the neurons in there do the same thing at exactly the same time. Okay, so all the neurons in there work in unison. Okay, it'll make things easier. So let's zoom in, and that's what you're seeing here. So what you're seeing here is that the slices, you're seeing the slices that we're collecting, and this is the piece of the brain we care about. And the important thing is that we're acquiring slices in an interleaved fashion, which means the TR starts, and then we're going to acquire 13, then 15, then 17, then 19, 21, go back down, 2, 4, 6, 8, etc., then 14, then 16, then 18, then 20, then 22. Okay, so we're acquiring the data in an interleaved fashion. We take every other slice of the brain, and it takes 1 second to do that, and then the second half of the TR, we acquire the remaining slices. Now, see, here's why this is important. Again, let's assume that all neurons in here do the exact same thing. So let me show you what would happen. See the black line? That's the neurons inside this piece of the brain responding. In fact, this is the bold signal inside that little piece of the brain. Let's just assume that across that whole piece of brain, the bold signal is exactly the same. And the truth, if you could go in there and look at it and see the reality of the bold signal, it's this black line right here. Okay? So that's what the brain is doing. However, because we are acquiring the volume a slice at a time instead of all at the same time, this introduces noise in our data. Let me show you what I mean. So in this particular experiment, each volume is acquired every 3 seconds. So from here to here. So this is the first TR, this is the second, this is the third. So we start the TR, and then remember we're acquiring slices in interleaved fashion. So we're going to acquire 13, then 15, 17, then 19, 21, etc. And then we start from 0. So we're going to acquire 15 and 17 pretty early on in the TR, in the first half of the TR. And then a full second and a half is going to pass before we collect the data inside 16. So In the meanwhile, of course, the brain is functioning, doing stuff. So 15 and 17 are capturing the bold signal while it's slow, whereas 16, just because we're capturing it a little later, just because it takes time before we can get to slice number 16, we will capture 16 while the bold signal has already started rising. And then we will go to the next TR, and we will acquire 15, then 17, and then 1.5 seconds later, we're going to acquire 16. So again, just because of the order in which we're acquiring the slices, the slice that we acquire the latest always looks like it has a stronger signal. Remember, I told you, we stipulated that all the neurons in that part of the brain, the bold signal is exactly the same. Okay? But just because it takes time to acquire the slices, it looks as if the green slice, 16, always has a stronger signal because we acquire it last. And then in the descending part of the bold response, it's exactly the opposite. So here's the third TR. We start, we acquire 15, 17, and then it takes 1.5 seconds, half a TR, before we get to 16. So by the time we get to 16, the bold signal has gone down quite a bit. So 16 will look like now it has a much lower signal than 15 and 17. And I told you the real signal in there is exactly the same. And then we go again, next TR, 15, 17, and then 16. And again, you see that 16 always appears to have a lower value. It's only because we're acquiring data along this curve at a different time. In fact, if you were to interpolate these time points where we acquire the data, it would look like this. All the slices that are acquired late in the TR, they tend to have a big peak early, and then they tend to come down faster. The slices that we acquire early in the TR tend to have a lower peak, but tend to last longer. And this is entirely fake. It's entirely due to the fact that we take the data one slice at a time. And of course, while we are taking the pictures a slice at a time, the brain is changing. So just by virtue of how we acquire data, we're introducing noise, because now it looks like the voxels here and here kind of have a lower peak, but more sustained, whereas the voxels inside 16 have this much higher peak, but much shorter duration. And it's entirely artifactual. So we need to fix this. In order to fix this, what we do is we interpolate. So we pretend, we essentially take these two values and increase them a little bit, and then this value and decrease it a little bit. And we kind of, it's as if we kind of squeeze all the values, pretending they were all taken in the middle. That's what slice timing correction does. It takes the values and kind of realigns them as if, interpolates them as if we had taken a picture all in the same instant. Now, I have to admit that slice timing correction is actually controversial as a pre-processing step. Whether we really need to do it or not is unclear and very debated. There are obviously some pros to it. I mean, in a sense, we are modeling better the actual bold signal. Because again, there will be some differences there that only have to do with the fact that we're sampling the bold signal over time. So we are, if we do slice timing correction, we are a little bit more faithful to what actually the brain is doing. However, there's a number of cons to it. For one, the ultimate effect of slice timing correction on the data is pretty small. And so if it doesn't do much to the data, why do you need to interpolate your data, right? Just don't touch it. If it doesn't do much, just don't do it. On top of it, it might actually worsen certain artifacts. So for example, if you imagine that for some reason you had a little spike in your data, by interpolating, you might actually smear the spike. So that would inject added noise into the data. It also has a way of interacting pretty unpredictably with motion correction. Sometimes, if there's motion in the data, it helps the slice timing correction. Other times it hurts it. And it's just not clear how the two, in fact, the two ultimately should be done at the same time, but nobody has cracked that nut. And finally, the truth is that there are other aspects of preprocessing and data analysis that might actually mitigate this issue anyway. For example, as you've seen, the problem is that nearby slices, just because they're acquired at a different time, will have very different signal. The truth is that we're going to blur across these slices. So we're going to average a little bit, and we're going to smooth across different slices. So by doing that, we're already kind of getting rid a little bit about the slice timing correction. And there are many other things that we routinely do that end up helping with this problem. However, I should say that if you're doing a task-free approach, then it is conventional to do slice timing correction, mainly because then you could imagine that there might be systematic differences between the parts of the brain that are collected, say, early and those that are collected late inside LTR. So in task-free analysis or in resting state analysis, it is routinely done.